try to rank our customers. Okay, so certainly machine learning techniques have been showing quite promising results in this regard. So let me just go to that. What I will do is use the full screen mode. Yeah. So this is actually how a sample data has been taken. This actually has been taken from this link. It's the data.london.government.uk, and this is a data of 789 customers. You can easily find it through this link. The data as such is actually having some of the missing values, some of the repeating values are also there. So there is always we may have to do a bit of a data pre-processing, and once the data pre-processing is done, we may have to normalize some of the features. Now, normalization is something which is important, because sometimes what may happen is that if you want to derive a function between the different variables, for example, yesterday I told you about a situation where you had various parameters such as number of bedrooms, age of the house, and then the price is the output, and similarly we can have other parameters like the locality and all. Okay, so but in that one we may also have some other factors. So all these different set of variables that we are using, they may have a certain range of minimum and maximum values, and it may just so happen that if you have a huge variation in this min and maximum value for the different variables, then we may suddenly find that the function the fitting problem may start occurring. So as a result of which, it is always a better idea to normalize the features first, so that all the minimum and maximum ranges for the different variables are with a close approximate. Okay, so so this is what we do. Okay, let's just look at the data. So this is how actually the data is looking like. So the data is actually is in this way, that every half an hour we are collecting the data, and we are recording the data for the entire year. Okay. So every half an hour means we have 48 data in one day, and then 365. So for each customer there will be 365 into 48. So that's why we have the patterns. And then what we have done is the data can be plotted, and the data is plotted for daily consumption, and not only it has been plotted for the weekly consumption. So it is just showing the pattern of the two customers. So it is for the pattern of the customer number 443, and there is a pattern for the customer 3856. And you can see that by looking at the daily pattern for the weekdays, and in the weekdays itself, if you want to find out the weekly consumption, then there is a strong correlation. For example, if you look at the Monday data, so if you look at the Monday data from the daily consumption, then I'm not denying that they are different. Of course they are different, but you can see that initially, in the initial time period, the value is low, then in the middle it is high, then in the evening part you will see suddenly a peak. Similar kind of pattern can be found in the second one also. Okay, there is some distinguishing factors. For example, initially here you might see a peak, initially here there is no peak. So that depends from customer to customer. But again, you can see that in the week 1, week 2, week 3, and week 4, so for about a monthly data has been plotted here, and you can see a strong correlation between the different weeks also. So that is one of the important thing that data visualization can provide you. Sometimes if a huge amount of table of data is just in front of you, you may not be able to find any interesting fact from the data. But once it is plotted, you may suddenly start seeing some of the patterns which can be addressed properly. Okay, so so the idea is that there is a representative curve method which has been used. So as you can see from the earlier graph, that the daily consumption pattern changes from customer to customer. So this actually signifies a pattern in the time that how the power consumption is done by a particular customer from human activity. And by analyzing the power consumption, we can do it on a daily basis, we can do it on a weekly basis, we can even do it on a seasonal basis, and then we can identify the patterns. One important thing that you will identify here is that this data is actually huge in number. So we have already said that we have about 365 into 48. That is the amount of the data that we have for one consumer, and then we can have a lot of consumers here. So if you go into that link which I showed you earlier, you will see a lot of customers, and then suddenly you can see that the data can become very huge. Do we have to do our analysis on that entire piece of data, or should we try to reduce the dimensionality? Reducing the dimensionality is always a good thing, because that once you have reduced the dimension, it allows you to concentrate on specific amount of data rather than looking at the data in the entirety. However, one of the other important thing that has to be make sure that once you are doing a dimensionality reduction, then the dimensions, the reduced dimensions, should be able to hold the important or relevant information that was there in the entire your entire data. Okay, so the previous data, which was compressed using a dimensionality reduction technique, the reduced data or reduced dimension should be able to capture the relevant information out of that entire data. Okay, so there are different techniques which we use to identify that part. For example, there's a variance and all, but I'm not going into that. But you can always go with the dimensionality reduction techniques. There is a PCA technique and all. So that has been used, okay, to reduce the data, and that is called as a representative curve method here. So what you can actually do is that you can see here that we have about 48 data. Okay. So this is the for every half an hour you can see there is a specific power consumption in kilowatt hour, and then you can see there is a value. What you can always do is you can represent these values either in the form of a mean, or you can do some sort of a standard deviation and all. So you can even represent them with some points. That is possible. Okay. So that's what I've written here, that according to the representative curve method, the 365 values in the given time period, it can be replaced by either a mean or a standard deviation across a time period, since they are very close to each other. So what you may eventually find out, that rather than showing this big lines for each customer, you can actually show it as a representative curve using this triangular dots that will actually signify the representation curve for a customer. So for moving forward, we can work with this kind of a data. Now the important part is where this data, or why this data can be of any use. So as I already said, that we can use this data to find the suitable customer for our demand response program. So what essentially happens is that if you have got some knowledge about the spot market for the electricity, what essentially done is that it's generally a day ahead market. In India also it's a day ahead market. So what is being done is that there is always a bids for the supply, and there are bids for the demand. And in the spot market, generally these bids are given by the different generations. So this generation could be from renewable, this could be from oil based, coal based generation, natural gas based generation. Then there is a demand from the different distribution companies, and then based on the demand, and the supply, spot um, bidding is done, and then wherever there's two bids cross with each other, for example, the generation bid and the demand bid. The generation, I mean, the supply and the demand, wherever these bids cross with each other, um, that point determines the price value for the power. It is called a spot market price for the power. So as you can see that the amount of the price that is, and then what generally is done is that once this market price is being decided, all the generations which have decided to supply the power below this market price, their generation is price is actually accepted. But you may see that the generation companies whose bids are accepted, they may not be able to supply the power at the same price. Some may be supplying the power at a lesser price. For example, wind and all, they may be able to supply at a very lesser price. Coal might be slightly higher price, then natural gas might be even slightly higher price. So the idea is that once our demand source of starts increasing, then the utilities go from one generation supply, and then steadily it um, gradually, as the demand increases, it fires up the next generation station. So what you may have to do is that as the demand increases, you may have to go for a slightly costlier operation for the generation. That is being said here by the first point. Okay. So what the utilities can do in order to avoid that scenario where the costlier generation may have to be brought online, they can always provide an incentive to the customers that if they can change their consumption pattern in a certain way, so that at the peak load periods, if the consumers are able to reduce their consumption, then we may completely bypass this possibility of going to the costlier generation. And then the idea is that these customers or these consumers can be a part of this demand response program, and they can affect the load, and they can affect the demand response on the load curve, either by shifting their load to some other time where the peak is not there, so that we will eventually have a peak reduction, peak, which is also called as a peak shaving or energy reduction. Okay. But once again, as I said, that you may have to identify those consumers. You cannot just simply uh, randomly pick some consumers and tell them to reduce their energy consumption. You may have to pick certain consumers based on their consumption pattern. So that is one option. So that is basically selecting the suitable customers for demand response program. Second could be the electricity tariff setting. So the consumers, based on their based on their consumption, they may have to be divided into different price slabs. So existing price practice includes tariff based on the point of connection and time and day of the tariff. So frankly speaking, in India, we don't have this thing. We have a flat electricity so far. But in many other countries, we also have noticed that the tariff setting changes from time to time. And as a result of which, you may see that there are different price slabs. So if you see that some consumers are trying to run their washing machines in the evening when there is a sudden increase in the load peak, then there is a possibility that these customers who want to run their equipments during that peak load time, they may have to pay a higher tariff price. Similarly, the same thing is now being researched very extensively for the EV supplies also. For example, in the electric vehicles, the idea is generally that the consumers, they are actually trying to um, take their electric vehicles in the morning, and then evening when they come back to their homes, they can plug their vehicles back into the grid system, and then they can charge their electric vehicles. But as we discussed, that generally in the evening time we see a peak in the load, So we can provide an incentive to the customers by setting a higher tariff price in the evening. So that way, customers will always also have the option to charge their vehicle maybe during the daytime when the electricity tariff is less. So this kind of a customer pattern behavior can actually lead us to decide the tariff settings also. So that's just the applications which can be considered. I will be mainly showing you the applications from the first demand response perspective. So yesterday I discussed that once you have the consumption pattern of all the customers, we may not want to use the entire thing for as a deciding factor that which customer should be used. So we may have to extract certain features. Okay. So these are some of the examples of the features that you can extract. For example, you can always use a mean consumption, mean power consumption, that is self-explanatory. You can always try to look for the peak power consumption. So some of the customers you might see that they may not be able to, they may not be extracting a lot of power or consuming a lot of power, but whenever they are consuming, they're consuming a very high amount of power. And if that high amount of power comes during the peak load time, then that may cause an issue. Okay. So you may also want to see what is the peak power consumption. Then again, you can have a max to min ratio. This could be also one of the features that can be extracted. You can give them a seasonal score. For example, from season to season, how the patterns are changing. Generally, in the winter time in the Western countries, you may see a higher peak compared to the summertime. In India, we have a reverse. So in the summertime, you can see generally a peak because of the increased use of air conditioners compared in the winter time. Then there could be a ramp rate also, and then volatility. You can use any other feature also which you think could be of use to you. For example, you can use a standard deviation. You can also compare from one particular customer to another particular customer. So you can use it that way. Just a second, I've got a comment. So I just Gururaj Vishwanath has asked that if a customer violates from the commitment to a demand response, then whether he will be penalized. See, generally what happens is that the customers, the penalization is not generally in practice. What the customers they do is that what the utilities or the distribution companies, what they do is generally decided based on the tariff. Okay. So if the consumers, if they are given a possibility to reduce their peak shaving, then they get the option of either reduce bill, which can always be monitored. Okay, and if they're not doing it, then they have to pay a price on the decided tariff itself. Okay, so that depends from the distribution company to distribution company. Okay, but generally there is not a concept of penalizing as such. Okay, I have not heard about it so far. The only thing that I've heard about is that if the customer becomes a part of the demand response, they are always provided an option that you can shift your load to that one. But if it is very urgent, you have to use your washing machine at that particular time, you have to charge your vehicle at that particular time. You cannot deny the service to a customer. That is a number one rule for any utility or distribution company. So you cannot deny the service. If you have to use the service, you might as well have to pay a higher price if it's a peak load, but you cannot deny the service. Okay. So hopefully I answered your question. Moving forward, so this is okay. So there are a lot of libraries which are available for machine learning studies. One of the most common one you might have seen is the scikit-learn. They have a lot of different modules available with them. We can use clustering, regression, classification, deep learning, a lot of things you can do out of it. If somebody is interested, you can let me know later on. There is a very good few of the hands-on kind of channels which are available in YouTube, so I can refer some of them if you want, where you can just practice some of the ML applications. Then MATLAB has also pretty elaborate toolboxes with them. And then you can use the different toolboxes in the MATLAB for your studies. They also have host of different applications ranging from machine learning to deep learning and all. So the idea is that what we do is that once we have taken the different features, so different features, as I said, are like this. So what you can do is we can take different features. For example, we can take mean power consumption, and we can take max to mean ratio, or mean power consumption, or peak power consumption. We can take two features at a time, and then we can just plot for each customer. Okay, and then based on the plotting, we can rank them according to their importance. Rank the clusters according to the importance. For example, I'm not going into the detail of how the ranking has been done in this particular case. I can always give the reference to the paper. There you can read it much in detail. But each cluster, there is given a rank, and then what we do is the score for each customer is stored, and we can tabulate it. And then finally, the total score for the each consumer is decided. And the final score, it can be sorted in the form of a decreasing order, and then the score based on the decreasing order of the final score, you can choose either the top 20, top 10, or top 15 customers, which can be a part of your demand response program. Okay, so let me just show you how it is done. So these are the 10 different cases, okay, which has been considered. Sorry for the small font. This is actually taken from paper, so it came out to be a bit smaller. But you can see here different dots. Each dot actually is showing you the two different features. So, for example, in the case one, it is mean versus peak. And in the second one, it is mean versus the max to min ratio. In the third one, it is the mean versus the seasonal score. Fourth is mean versus the ramp ratio. And then similarly, you can take rest of the other ones also. For example, you can take peak versus the mean ratio, and so on. So you can take each customer, and then each dot signifies to each customer that they are belonging in these kind of clusters. Okay, so that way you can have 10 different kind of cases. You can have more of them if you want, but it came out to be 10 cases in this particular case study. So you can plot them, and then based on it you can do some kind of a scoring. For example, if you're doing x and y, where x is the feature 1 and y is the feature 0, then C1, C2, C3, this actually defines the customers. So these are the values for the first 15 customers, and then depending upon the position of this customer, they're getting the points. Okay, so in the F1, F0, they're getting the first 1 point. F1, F2, they're getting 1 point. F1, F3, again, they're getting 1 point. In F1 and F4, so two different features, they're getting a higher point here based on their consumption, and then depending on this, they get a rank. This part is completely dependent upon the researcher, how they want to do it, how they want to decide the ranking. There is not a fixed rule. So, for example, if you are very concerned that the peak power is the utmost requirement for you, that needs a very careful attention, then you can give a higher rank to that person, which is having a very high amount of peak power. Okay, so that becomes the number one priority in your list, and then you can rank that customer very high, and you can offer them to become a part of your demand response program. That completely depends on your instinct and your the way you want to deal with this sort of problem. Okay, so these are the scores of the first 15 customers, and then similarly the scores for all the customers are collected, and then based on that, the top 15 customers have been arranged in their decreasing order score. So you can see here that the score for the 38 customer, and some of the 38 to actually 574, these customers, they are pretty much all the same. So based on their total score, now you can choose that these 15 customers can become part of your demand response program. So that's just one application that I wanted to show you. Okay, So this is an example which signifies the clustering method, which can be used to identify, and then different ML techniques can be used to do that. Okay. Let me just try to show you one more application. Is it done? Okay, one more confirmation I want to have. I have to have another half an hour or so, right?
Yes, sir. Yes, sir.
In the email that was sent from the host, the starting time was given, but I forgot what is the end time.
Okay, after 12:30, even half an hour more. If you.
Deepak, are
Yes,
you
sir.
available?
Yes, sir.
So Deepak, can I present until 12:30? Is that
Yes,
fine?
sir. You can continue till.
Somehow I'm not getting your voice, so if you can just respond me over chat.
Okay, sir. You can continue till 12:30, sir.
Sir, you can present up till 12:30.
Okay, fine. So I will maybe for another 20 minutes or so, 25 minutes. I will present another case study that is actually done by one of my student. That, just okay, yeah. So yeah. So this is actually one of my PhD student. So he has he's been working in this area of microgrid protection and using deep learning techniques to identify some of the interesting phenomena in the microgrid. So I will give a brief intro first about the microgrid protection. What is the motivation? What are the challenges and gaps in the existing research? What kind of study he has done? And then his proposed method. Then I will show you some simulation and result analysis also. So I've just taken his presentation. So what microgrid essentially is that there is a host of distributive energy resources. For example, there could be wind, solar, battery, EVs. EVs can work either as a load or as a source also. Then you can have DGs and all. So these are the different sources. Then we have different kind of loads. Loads can again be EV. It can be battery also, households and the industries and so on. And then generally this kind of microgrids they can have their own kind of a smart grid environment integrated among them. For example, they can be connected to the energy market. They can be having a specialized kind of a method where they can have their load forecasting and all based on the weather. And then this microgrid can also be connected to the other microgrids. That is always a possibility. And what generally in the microgrid they do is they can be connected to the main utility grid also. So what the utility grid looks like when they're connected to this grid, it does not take a lot of part in all these different sophisticated smart grid kind of activities. It sorts of stay aloof and then just see this microgrid as either a generation unit um, or as a consumption unit. So there's like a variable load. Okay, for this grid, this microgrid is nothing but like a variable load. Okay. There is a possibility that this load information can be communicated to the grid, but let's not discuss that thing in much detail right now because that will require a separate kind of a discussion on how the microgrid operation and control is. But as you can see, there is a switch here, so it can be on. When we say on, that means the grid is connected to the microgrid, and when it is off, then the microgrid is not connected to the grid, so it is working in an islanded kind of a scenario. So Based on this thing, you can see that the microgrid can operate in two modes. It is a grid connected and it's a islanded mode. A lot of studies are going on that generally in the islanded mode of operation, if the microgrids are not equipped with very sophisticated control hierarchical structure, then as a rule of thumb, whenever there is a islanding, the different distributive energy resources which are there in the microgrid should simply cut down their supply. Okay, that's a simple rule uh, um, for the microgrid operation. I will be, just give me a second. Yeah, so that's essentially what the microgrid is. Let's just go further. So the motivation is that the microgrids are the localized grid that can be connected, disconnected to the main grid. I think some of these things I've already discussed, and you know about it that microgrid they are generally important nowadays because of the efficient, low cost, clean, secure, reliable energy supply. They also increase a lot of robustness among the grid, because what may happen is that sometimes due to the natural calamities and all, or due to some power failure, if some of these local microgrids are available to supply the power, then you can see in the contingency scenarios, you may still have a reliable supply to your community. Okay. When I say community, that means the important or critical loads, such as the critical loads can be your hospitals. The critical loads could be your superstore, which are providing necessary food items, water, fresh vegetable supply, milk supply, and all. So these could be your critical loads. Okay. So so the challenges that we have is that we of course want a safe and reliable operation of the microgrid. And sometimes what may happen is that there could be different phases. Now, microgrid, one thing you will generally notice is that there could be various unbalanced scenarios, because the loads are very dynamic in nature. So the microgrid may be even operating in an unbalanced kind of a scenario where some of the loads in one phase are certainly higher than the rest of the other two phases. So that is a very common thing which happens. So if there is a phase tripping and all, then we have to of course protect the microgrid. And not only this, if there is a phase, for example, if there is a fault in one phase supply, you may continue to supply the power to the rest of the other two phases. Okay. And you can might have as well as have an option that if the enough power capacity is there, then the consumers which are already there on the other phase which has been tripped, they can be moved to the other two phases. So that there could be a possibility. Okay. So the idea is that we can have a selective phase tripping in the event of the fault. In order to trip the selective phases quickly and accurately, it's very important that we should be able to detect and classify the type of fault. We have to make sure that which phase actually has tripped. And I was talking about that yesterday also, that you have to identify the phase type, okay, or the fault type. And this can be done, of course, this can be done by using sophisticated relaying kind of a techniques. But one of the major problem you will see that when you are using the same relays which are used in the grid condition, and then if they are simply used in the microgrid scenario, they may not operate very reliably. Okay. And one of the reason is that the current ratings for the relays can be significantly different in a microgrid environment than in the grid environment. Okay. And it is generally not possible that you can design the relays based on each grid requirement. So you have to provide some sort of other way to identify that which fault has been done. Okay. So the ratings for the so in a nutshell, what I want to say is that the relay ratings can be significantly different for the grid kind of environment and for the microgrid environment. So the traditional relays may not feasibly or reliably operate all the time. So that's why we need to have sometimes some intelligent and fast acting methods. So what we are essentially doing here is that we have identified some of the gaps. So in this gap, we have seen that AI techniques which can be used, which have been used for the state-of-the-art microgrid fault detection and classification, they are generally machine learning based. And then in a machine learning, if you're using, then one of the important thing that you have to do is you have to do the feature extraction. So whenever you are seeing three waveforms of voltages and three waveforms of current which are coming from a particular section of the microgrid, you can't just simply take these three voltages and currents and then try to detect what kind of a fault is there in case of any contingency. What you may have to do is you may either have to find out a positive sequence component or negative sequence component or a zero sequence component in case of a grounded fault, or you may have to find out the harmonics, or you may have to find out a particular total harmonic distortion, and also different features you have to identify to pinpoint that what kind of fault it is. So basically your data comes to you, and then the feature extraction is another thing which has to be done. For example, there could be this DFT process which you may have to do on the collected signal for a certain window, and then that feature extraction can be used for fault identification process. Okay, so there are a few papers which have very nicely actually have given a review of some of this process. So if anybody is interested, I will request the host to drop me an email, and I can reply with these papers which identify some of the feature extraction process. Okay, now the problem with this feature extraction is that this data is coming to you continuously, and you have to extract this feature, and then there's a DSP which is involved in extracting this feature. But whenever this feature extraction is going on, you have to use a lot of computational resources. So there's a burden. Okay, so there is a burden on the DSP itself, and you have to do it every time window. Okay, so that becomes a bit computational burden. So the idea is that with the deep learning, it can be solved easily. Okay. Deep learning, the advantage that it has over machine learning is that with the deep learning technique, actually, there is no need of feature extraction. So you can supply the raw data as it is. And then this deep learning technique actually try to learn from the different patterns of the raw data, and then it can be used to identify the features appropriately, and then it can be used for classification purposes. Okay, now my question to you is that deep learning has this advantage. Okay, is there any disadvantage you think is there of deep learning technique with respect to the machine learning technique? So you may not want to answer me now, but you may reply in the comment box, and then if there is any time left for the Q&A, we can discuss on that. The question is that I just told you the deep learning technique, one advantage is that there is no need of feature extraction. We can easily supply the raw data itself, and then we can classify it. Okay, the machine learning, you have to do the feature extraction in order to do the classification. Okay, so is there any disadvantage do you see just from the statement which I made for the feature extraction? Is there any disadvantage in the deep learning technique which is not there in the machine learning technique? Okay, so you can reply me in the comment. So the data set which can be, of course, this is one disadvantage. So don't reply to me with this disadvantage that data set can be huge and all for deep learning. Of course, it is there, and the good thing is that we have resources nowadays to carry out such huge data extraction, and for training and testing purposes. We have various other methods like distributed computing also, which is there. Okay, so you can have the training and testing for the ML model. Now, generally, it's said that for ML model you may not require a lot of data set. That is true, but for deep learning we require huge data set. That is true. Okay. But that is not something which I am looking for. Okay, so I will look into your comments. Some of you are commenting, so I will look into that comments later on, otherwise it will distract me. So one of the other interesting thing is that model may remember the data set instead of getting trained. Okay, for example, I will give you a very simple kind of a way that suppose you're going from your whatever your hostels or your home to your department every day. Okay, and then suppose there is a new person who has joined the institute, and then every day the person is going from the same route to the from the same route it is going to from their home to your department. Okay, and then suddenly one day they might observe that there is a road work which is going on and the main road is blocked. Okay, now is there a way by which they can still reach to their department? If the person has already gone through some other routes, then yes, there is always a possibility that the person, if there is not a possibility to reach to your destination through the standard route, you can always use some other route. But the person has to be, he or she has to be exposed to that route earlier. Okay, now you can always take out your mobile and then try to see another route. That's a different thing. But I am just saying that previously when the apps are not there, the person has to know about some other different ways to reach to your destination. But somehow in the deep learning technique, if you are not allowing the deep learning technique, when they're trying to learn from different patterns to reach to a conclusion, they may tend to remember this kind of a path. Okay, so you don't want that to happen. You want the deep learning method to be trained in a way that in some case, if some important feature is missing or that feature is not having relevant information, you should try to choose some other way also to reach to a conclusion. Okay, and that is what we call as a dropout rate. So sometimes what we do is that we give the data to the deep learning technique, and then we tend to do some sort of a dropping of the data. So some data will be dropped from time to time, and that will just allow the deep learning method to look for alternative options to reach to a classification conclusion. Okay, so that dropout rate is also used, and it is not very difficult actually. In the deep learning method itself, in the scikit-learn, you can decide what kind of dropout rate can be there, and that is also part of the hyperparameter tuning, which can be done. Okay, so you can see that there are when the student was actually identifying, he found out that there are different methods which are available. For example, there are wavelet based data mining method, and then which are used for the microgrid protection. There's some methods which are available for the microgrid differential microgrid protection scheme. There are possibilities for different microgrid faults, identifying detection and classification. Okay, and you can see that there are various kind of test systems and the protection techniques which are used, and there are different data sizes also. But one of the things that we identified is that deep learning is not being used very appropriately in some of these methods. And not only this, sometimes if you're using machine learning techniques to identify different types of things, for example, if the data is given to you, the data may also have some noise in it. Okay, now there is one possibility that you can filter out the noise, or you can use some other machine learning technique to identify that, okay, this is a noise signal and this is the main signal. You can choose a machine learning technique to distinguish or classify the signal itself. But once again, if you're using a lot of different machine learning techniques to identify different things, it can be time consuming. And that was some of the gaps we identified, that the techniques could be of useful. They may be having high accuracy also, but they may certainly be very computationally burdensome. Okay, and we need a very clean and a very efficient kind of algorithm. So that way we have actually different this stochastic gradient descent based algorithms. So we have RMS prop, we have Adam. I'm not going into the details of these. Okay, There is an Adam, there is AdamX. Okay. So various ways are there um, to do the DL algorithms. So what we have essentially done, we have used actually all four of them, and then tried to identify that how we can use this deep learning method. So what we have done is we have simulated first of all various three-phase faults. Okay, in the simulating block using the external trigger. And in the next few slides, I will just show you some of the PPTs which show the faults between the line 671 and 632. And of course, this is connected to the main grid. We will also consider the case which are connected to the islanded scenario also. And then the fault is created at 200 feet from the bus 632 and 1800 feet from the bus 671, which is corresponding to the 10% length of the feeder section. So we are not just identifying the type of the fault, but also the location of the fault. Okay. So this is how the test system looks like. This is a slightly modified IEEE 13 bus system. So we have a wind generator. We have, DFIG is there, PV is there. Of course, this is the main utility. We have a DG system also, and then different kind of loads. We have capacitors also, so switchings can be provided. So this is our proposed microgrid protection system is. So what we are doing is we are taking these measurements at two different buses, and then all these VA, VB, VC, and IA, IB, IC, and of course the neutral current. So total 7 parameters are being measured continuously, and they are given to a deep learning based fault classifier. And then what we are doing is, if there is any fault in the system, then we are trying to identify that what kind of fault it is first of all, and then where in between these faults are being located. So based on that, we can give a trip signal. We can either try to trip one of the phases if it is just a single line to ground fault. If there are two phases, we can trip two of the phases, and if there's a three-phase fault, of course, then this line is not operational at all, and you have to just remove all the three phases. And then the topology itself can be two types. It can be either grid connected, it can be islanded. Just to increase the number of the test cases itself, what we have done is that this fault which is being applied, it can be a bolted fault with the zero resistance through it. So you might have studied about the fault resistance when you're doing the basic power system protection course, power system analysis course. So that impedance value we just have taken a different numbers. Okay, and then the fault location we have tried with 3 different options. We have tried either with a 10% from a particular bus, or a 50% or 90% of the section, and then we are just trying to identify that this is actually for the training purpose. Okay, and for different kind of faults have been applied. You can see here. So eventually, what we are trying to identify is which kind of fault is there and where the fault has been applied. Okay. Yeah. So this just tells you that there could also be a no fault case simulation where there is a loads at bus 634 and 671 are disconnected. So if the loads are disconnected, that is not essentially a fault in the system. That's just a small disturbance. Similarly, another disturbance could be just a capacitor bank which is being switched. That cannot be considered as a fault as such. So we may also have to identify that our deep learning method, it is able to distinguish between a fault case and a non-fault case. Okay, that is also important. It should not happen that if there is any simple random load change, then it can identify it as a fault and simply disconnect some of the phases. This should not happen. So these are simply the waveforms which have been observed. I am just showing you some of them. So this is a line to ground fault which is happening at this particular instant. So these are the voltages and current waveforms. Sorry, we don't have the. This was his previous presentation. I have asked him to make some changes, but I have the updated presentation, but I forgot to use that one. So here is the voltage. This is the current, and this is actually how the line to ground fault current looks like for the negative sequence component. So if you're using a machine learning method, you might as well use this as a feature. Okay, but we are not using right now this as a feature. Similarly, if there is a line to line fault, if there is a double line to ground fault, and if there is a triple line fault. So we have three different kind of cases, but these three different can change from one phase to another. Okay, so there will be multiple number of cases. So software that we're using for this thing is simply the MATLAB Simulink. We are designing our system in MATLAB Simulink. We are collecting the data. Once the data is collected, we have labeled it and we have cleaned it using Python. And then for training and validation, we are simply using TensorFlow, Keras, and Jupyter Notebook. Standard things. Hardware which we are using is i5 and 8 GB RAM. This can be the reason why I've mentioned this is sometimes people in deep learning, they are also interested to know that what kind of hardware they are using. So just want to mention this. And then the split in the data that we are doing is we are doing 80% training and 20% we are doing for the testing. Okay. So there are a total of more than 13,000 samples with 14 input columns. You can see what these 14 input columns will be in a second. So the input layer that we are providing, so he's okay. So he is also providing a negative sequence current. Okay. So he's not just providing VA, VB, VC, but also negative sequence. That's why the reason he was providing that negative sequence. But I remember our discussion, he said that the negative sequence is not making a huge impact. So even if you remove this, he has actually done the study without the negative sequence also. And even in that case, he was getting a good observation. So the number of hidden layers he has taken is 10. This is completely randomly chosen. We can even increase or decrease, but he just found out that 10 is optimal level. Each hidden layer has about 60 units. We have used a dropout rate, which I just told you what it is, as 10%. The output layers are 10 units. So these are the classified outputs. So remember what outputs are. The outputs are the different kind of faults. The activation is hyperbolic tangent, output classifier is softmax. We have used different performance matrices here and different kind of optimizers. So we just want to see that how these optimizers are performing in based on this performance matrix when it is given these inputs and asked to provide this much number of outputs. Okay. So this is how a categorical type looks like. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are 10 types of outputs. You can see here. So that's why our output was 10 here, output layer, classified outputs. And then if the phase A and B is involved in it, then we just give 1 to both phase A and phase B. If not, then phase C and ground are simply 0, and then this is class 0. So similarly, we have this 10 classes. So these are the results which have been shown. So these are the model training accuracies. So you can see here that ADAMX is actually performing quite well in terms of different accuracy, and these are the number of epochs. So we are using around 200 epochs, and then it is reaching up to 90% accuracy. These are the model training losses. So in the training losses also we can see that the ADAMX is performing better. And this is this confusion matrix. If you are not aware about confusion matrix, I highly encourage you to look online. It actually tells you that if the AB fault was there, then how many times it was able to identify it as AB fault. So out of all the different cases, it was able to identify it as AB fault for 255 times, but for 9 times it identified actually wrongly as ABC fault. Okay, so this is what it is. So you can see there is a score which is being given for different precision, recall, FN score, support. So you can see average coming out for all of them. And these are the ROC curve. So this is the fault positive rate and true positive rate. If you don't understand this right now, don't worry about it. You may have to go through a bit of a understanding literature review and all to understand this kind of things. These are for RMS prop, NADM, for ADAMX. So we have done this study for both the grid connected as well as the islanded mode. So this is for the islanded mode of operation. these studies. So this is a mean absolute error. So as I said, we are using the model accuracy, model training loss, and absolute error, mean absolute error for finding it out. So this is for the islanded mode. Islanded mode is a bit trickier because, as I said, that the current values may suddenly change a lot depending upon the different scenarios. Okay, and that's how the F1 score is for the islanded method. These are them. I will quickly skip them. So this is an important thing. So comparison of the different deep learning algorithms. So we have just identified that out of the 4 DL algorithms that we have used, actually for fault or no fault accuracy, ADAMX is able to give a very high percentage of around more than 97% of accuracy, whether it's a fault or no fault. When I say fault or no fault means there could be a scenario that there is a simple capacitor switching or load change. In that, is it able to identify it as a fault or not? And of course, what kind of fault it is. Okay. So that one, it is giving 97%. The grid connected one, it is giving 96%. Islanded, it is giving up to 94% accuracy. Yeah. So with this, actually, I would like to stop. And I will look into your comments that you have sent. If you have any questions, you can also ask me now. So some of you have actually, so my question to you was that machine learning technique, you have to do a feature extraction. Deep learning technique, you don't need to do a feature extraction. You can directly feed in the data. But with this statement, is there any disadvantage that you can see with the deep learning technique? So let me just try to see what some of you have responded. So DL needs high computational, high-end processor compared to ML. Yes, that's true, but that's not exactly what I was looking for. Computational time is high. No, that is fine. That is fine, but we don't worry about the computational time as such. Further reduction is essential. Are you talking about the dimensionality reduction? In this particular fault analysis, we have not done any dimensionality reduction. Actually, we have just taken the data as it is. And Joshua, initial training must be difficult. Yes, it is difficult, but eventually it learns. Depends on the what kind of optimization technique you are using. So you may see that for some optimization technique it may be a bit difficult to train initially, but some of them they may quickly conclusion. Yes. We have used a simple deep neural network. No any sophisticated RNN or anything like that. You can always use a certain specific one like LSTM and all, but in this one we have not used it. Dropout is like missing data in the training. Yes. So what we are doing it is 10% data we will just simply randomly it will be dropped while training. So then it will force the deep learning to identify new ways to come to a conclusion. What do you mean 1D or 2D? The data is one dimensional only. So all the VAVB, VC, IAIB, IC are given like one dimensional data. Okay, so the reason why I was saying that yes, the accuracy may be affected by dropout, but you may have to see actually that you are not making a system which may perform well for your data, and then suddenly if somebody else try to use the same deep learning structure for some other system, then it will suddenly stop working. You don't want it that way. Okay, so that's why the dropout is used. Islanded mode of smart grid is working in which area across India? Okay, so that depends. For example, I know some of the people from CDAC, they have actually established some of the microgrids in the area of Kerala, and it is currently working in the islanded mode also, as well as in the grid connected mode. I don't have any idea, Gururaj, if the Delhi islanding is implemented. Oh, you are telling everyone. Okay, so in Delhi, islanding is implemented, but I don't have any idea about that system. Okay, so I just want to answer the question which I asked. So the question that I asked was that in the machine learning, you have to do a feature extraction. In the deep learning, you don't have to do a feature extraction. But the problem with the deep learning is that it is doing a feature extraction internally. So you don't know that actually at which hidden layer or at which section, what kind of feature it is extracting. Okay. But in the machine learning, you know at which particular step the feature extraction and what particular feature is being extracted. So if you want to pinpoint the deep learning architecture, the deep neural network, that this particular neural network is identifying this particular feature, that collaboration you may not be able to do with the deep learning. Okay, and that becomes very handy if you are doing a research, because if you come to know about the deep learning method, if this hidden layer is working on this particular aspect of the feature, then you slightly you can tweak with the parameters for that particular hidden layer, but that is not possible. So that is the reason why that's a bit of a disadvantage. Prediction problem, Sabina. Unfortunately, I don't have a slide right now as such prepared for that, but you can see a lot of papers are there in the IEEE for the load prediction. Tons of paper for load prediction in the distributed energy resources. Yeah, you just search. You will be able to identify them. What is the main difference of data set and islanding with respect to each other? How it can be simulated? Data set does not have any change as such. We are still observing VAVB, VC, and IIBIC. The only thing is in the islanded mode, the grid side is disconnected. That's it. So in the simulation, you can just have the this block which is there, which you can simply trip at, let's say, 1 second or 2 seconds, and then you just keep on collecting the data after that. Smart grid scenario in India and working condition. I think Puducherry. Okay, I'm not able to. Maybe you're just telling everyone. Okay. I think in Pondicherry. Okay. So my comment is not able to understand this comment properly. The question. Lata Maheshwari. Weight initialization while training DL important. Any standard initialization technique? Yes. I mean, frankly speaking, if you're simply doing in Scikit library for the DL method, then Lata, you don't have to worry about the initialization. It just use the initialization itself, and then you don't have to do it explicitly by yourself. Okay, so you don't have to do that. Okay, but of course, if you're trying to write your own algorithm, then you may see that yes, initialization may have a certain impact. Okay, but if you're avoiding writing your own script and all, and you are using the standard blocks from the deep learning, then you can always use the regular optimization technique, and they will just do the initialization, weight initialization. Okay, so is dropout only a regulation technique in training? Yes, you can say it that way. It avoids the overfitting and all. There are a few more questions, so I will not keep answering one question. I will just try to answer the other questions also. What are the 14 columns of your data set in fault classification? So there are VA, VB, VC, IA, IB, IC, and then this negative section is there. And 14 columns of your data set in fault. So there are 10 of them which are there for the fault classification, and then there is 4 of them which are there for the different this location. That's why. Can we apply different architecture of NN for voltage stability? Yes, you can definitely do that. You can try using LSTM, you can try using RNN. Can you suggest some good coding online source for deep learning and so showing its application to power system? That for power system as such, I'm not too sure if there is anything available. You will have to work it on your own. But for coding, you can always go through some YouTube channels. For example, there is something which is called as, one of my students told me that this code basics, this person has a YouTube channel. It is a very good one, and he explains it and shows you the code, and then you can use it, and then he also gives some exercises you to try upon. So you can look into that. That is code basics. If you just type in YouTube code basics, you will see some libraries, and then once you have identified how to use them, you can always try these techniques on a power system data. And if you ask me that how you can collect the power system data, there are a lot of open databases. You can download a set from Kaggle, you can download a set from the government data banks, always possible. AMR smart meter has many drawbacks. Why this technique is used in India, especially Lucknow areas, many drawbacks or so. I'm not aware about the specific of it. Sorry. So AMR. Are you saying AMI or AMR? So one of the reasons why smart meter data is if you see the drawbacks in the smart meter data could be because they may be they may have some problems with respect to their automatic meter reading. Okay. Yeah, Sharad, I don't have any specific information about that. But I think one of the main reason why it has been done is just to avoid avoid a lot of human interfacing with the meters. And if there is any tampering and all, then it can be directly communicated to the utility. Okay. Okay, I think we are about 12:45 now. So Deepak, if you want to take over from here.
Okay, sir. Thank you. Thank you, sir. Am I audible? Hello, sir. Am I audible?
Okay, thank you very much.
Sir, I think you have some
Satya Prakash Pandey. Thank you. Hopefully, I was able to answer your questions. If you have any doubts, you can always give me an email at this one. I will just type it out. Okay. So you can just send me an email over here if you want any specific questions. If you want to even work in collaboration, let me know. Okay. Fine. So yes, it seems like there is some problem with my speaker.
Okay, sir. Thank you, sir. Sir, I'll contact you. Okay, sir. Thank you.
Can I just sign out and sign in again? I will just try that.
Okay, sir. You just check.
We had a wonderful session with Professor Prashant Agnihotri. Hope he joins again in a minute and hope we are able to convey our vote of thanks to him.